Okay, thanks a lot. Yeah, thanks a lot to the organizers for the invitation to come. So we saw on the first day, there was a nice picture about sort of hierarchies of models we have for rotating convection, from spherical shells to the closed cylinders we do in the lab to periodic boxes. And I think I'm going to be kind of taking the perspective that it might be the case that doing proper simulations in any of these domains is hopeless. So maybe we actually need something even simpler than the periodic box if we really want to get to the parameters of the geophysical objects. So what I'm going to talk about is sort of an experimental numerical technique that's an alternative to direct numerical simulations like we do in these geometries. And we're curious if we can use that to model turbulent flows at extreme parameters. And this is joint work with Steve Tobias, Curtis Saxon, and Rich Kurzweil. And I'll say at the outset, it's very experimental. Okay, Michael just asked me if we can trust the log lattice results. And the answer is no, because if we could, then it would be DNS, right? It's an alternative to DNS, but there's some promising results so far for very simple flows, and we're trying to extend that to more complicated realistic flows like rotating convection. So, okay, so we're going to start with just the basics of Fourier spectral methods. So regular Fourier discretization that you'll use in a direct numerical simulation, say of a periodic box, is just using basis functions that are Fourier series. And these are really nice because if we use a full Fourier series, that's a complete basis that gives us exponential convergence for smooth periodic functions. We also have the FFT, so we can do fast computations using Fourier series. And also, it's easy to solve PDEs using Fourier series because differential operators are diagonal in the Fourier basis, because these exponentials are eigenfunctions of the derivative. So Fourier-based pseudospectral methods are the method of choice still today for the world's largest turbulence simulations. So these are simulations by P.K. Young's group at Georgia Tech, where they've done 3D Fourier pseudospectral methods up to 32,000 cubed grid points now. And they run this simultaneously on 32,000 GPUs using the entire Frontier supercomputer. This is an image from an earlier simulation that's just 12,000 cubed. The 32,000 cubed, there's no point in even visualizing it, right? Because you can't see anything. But still, this only gets us to Taylor scale Reynolds numbers of something like 2,000, right? So the point is that DNS is just extremely expensive to really go to high Reynolds numbers. And the kind of back of the envelope calculations for this are that in homogeneous isotropic turbulence, at least, the dynamic range of spatial scales goes like integral Reynolds number to the 3/4. That's also what you need for the number of time steps to get dynamical time at the CFL constraint. So overall, these combine for a 3D scaling of your overall degrees of freedom in your simulation going like Reynolds number cubed. So basically, we just have to wait for computers to get faster to do higher Reynolds number flows, and this is happening very slowly. So that DNS we looked at today, that's an integral scale Reynolds number of something like 10 to the 6. But to extrapolate to the Reynolds numbers of planetary or astrophysical systems, that means we're going to have to wait many decades for DNS to be good. Okay, so the idea is instead to use an entirely different type of discretization, and it's going to be giving up a lot of nice features of a true Fourier series, right? So in particular, we're going to throw out the fact that we have a nice complete basis where we can prove convergence for general functions, because we're going to have to give up something in order to get a much faster method. All right, so the idea is to still use a Fourier basis. So our unknown variables are still going to be sums of Fourier amplitudes times complex exponentials. But instead of the regular Fourier series, where we take all of the integers as our set of wave numbers, we're going to take a logarithmically spaced set of wave numbers. So the idea is that we take our wave number set to be 2 pi over some large length scale L times some fixed spacing factor lambda to the power of n, where n is a positive integer. And what that means is that the number of modes we have then goes logarithmically with the dynamic range of spatial scales that these Fourier modes are resolving. So for reference, lambda could be something like 2, or it could be, in practice, we use something like 1.1, something in that neighborhood. And I'll say a little bit more about that. Okay, so this basis set, where you take this kind of decimated Fourier series, loses a lot of nice mathematical properties of the complete Fourier series. It's not a complete basis for smooth periodic functions, but it does retain some mathematical properties. So all of these things are true. So you still have like a reality condition. You still have that differentiation is just multiplication by the wave number. You can calculate an inner product just using Parsifal's theorem here. And you can do this sort of modified form of integration by parts under that inner product. So it has a lot of these properties that actually mean that for a system where the dynamics are separable over Fourier modes, the discretization in the log Fourier lattice should give you the correct linear dynamics. So we could think of this as a good discretization for looking at linear stability problems across very different scales. The question is it useful for nonlinear problems? Okay, and the answer to that is that it depends on this lambda. So in this log lattice, you can only have triads, that is where two different wave numbers actually add up to a third wave number in your lattice for certain values of lambda. And this is detailed in this recent paper by Ciro Campolina, which is like really a seminal paper in introducing this whole idea to the fluid dynamics community, I'd say. And he enumerated all the different cases here. So the things that work and actually give you triads on these logarithmic grids are choices of lambda that include lambda equals 2, lambda equals sigma, which is the specific plastic number in mathematics, or lambdas that satisfy this relation for any integers a, b, and there's all kinds of like detailed conditions here. The point is that if you pick something that satisfies that, then what you end up with are a discrete set of triads that exist locally in the log grid. So when you take integer wave numbers, right, every wave number can talk to every other one. So there's sort of n squared many triads that exist in the regular Fourier series. So we compute that product using an FFT. The idea instead is that here you would do a calculation that's entirely in Fourier space, but computing a nonlinear product would take order n time, where n is the number of modes you keep, because there's only a finite number of other wave numbers that any given wave number can talk to in this lattice. So you're basically removing highly non-local interactions from the wave number grid. And these numbers, a and b, that you pick, so those are integers that you decide ahead of time, say a is 4 and b is 7. You solve this equation to get a value of lambda, and then those ABs actually control sort of the width of the interactions in the triad space. So you talk to wave numbers that are 4 away this way and 7 away this way, or something like that. Okay, so this is the basic idea of what's now called the log lattice Fourier discretization. This is what it looks like in 1D, but you can apply it to multiple dimensions just by taking direct products of these. So you do this in kx, ky, and kz if you want, and then you get sort of these like webs of interactions of triads, where say in our 2D Fourier space, this mode will talk to all of these modes under a quadratic nonlinearity, but doesn't talk to all the other ones. So asymptotically, as we take n being large, the computation of the right-hand side in something like Navier-Stokes is still just order n, not n squared. Okay, so this paper by Ciro Campolina used this discretization in 3D, so take a direct product of this log lattice in 3 dimensions, and they used it to simulate, went too many slides. Used it to simulate homogeneous isotropic turbulence as a test case. So this has a lot of overlap with classical shell models for turbulence modeling, and there's some detailed differences. I'm not really an expert in that. But in general, they find that this works pretty well for homogeneous isotropic turbulence. So they get a nice inertial range between the energy injection scale and the dissipation scale. They get the expected Kolmogorov structure function scalings, and they get nice PDFs that look Gaussian in the inertial range and have broader tails in the viscous subrange, sort of indicating a temporal intermittency in the Fourier coefficients here, which is supposed to mimic the spatial intermittency in the isotropic turbulence. Yeah?
Is there an obvious reason that you can communicate right now why this should just maybe naturally work in something that's homogeneous and isotropic?
Yeah, so I guess philosophically you could say like the Kolmogorov arguments, and to an extension like the arguments in convection for diffusivity-free regimes, those don't actually use much about Navier-Stokes, right? Those are really based on like dimensional analysis and conservation principles. And those things are satisfied by the system as well, right? So you could think of this as it's sort of a dynamical system in Fourier space that only very roughly looks like Navier-Stokes, but it still has a lot of those same properties, so you might expect that that's why it works. And in terms of the spectral energy transfer, I think that's key. So in homogeneous isotropic turbulence, you have a local forward cascade, and so the triads that you're keeping in this grid sort of still allow those types of interactions between modes. Yeah.
So is the equivalent here of kind of a grid refinement study of expanding how many modes that you talk to and see if it matters for the final result?
Yeah, so that's a good question. I don't think there's a clear idea of how to do that, because what you would sort of want to do is maybe take this lambda parameter to 0 to get a denser and denser sampling of Fourier space. But as you do that, you're changing what types of interactions are actually allowed. So it's not easy to like keep the properties of the triads constant as you do that refinement towards lambda approaching 1. So yeah, I'd say it's not clear. Yeah, it's not obvious how to converge this. Adding more modes is giving you more dynamic ranges of spatial scales, but it's not actually giving you denser interactions in an easy way. Yeah. Yeah.
When you increase resolution, don't you kill computation with a stability criteria? Don't you need to decrease the time step?
Yeah, so that's also not super clear. It's a good question. Like intuitively, we would expect yes, that there should be something like a CFL constraint here as well. The issue, though, is that these lambdas are not rational numbers. So the powers of lambda are not wave numbers that are actually commensurate on any box of a given size. So there's not really a sensible grid representation of the solution here, because it's sort of a whole mix of wave numbers with incommensurate frequencies. So it's hard to actually say like what a point-wise velocity amplitude is in this solution. I don't think anyone has super carefully looked at this. I mean, what I'll show later does have a lot of temporal restrictions are definitely a difficult thing here. And there are some ideas of like quasi-CFL conditions that I think might help with that, but we haven't really figured that out yet, I'd say. Yeah.
You say wrong slope. How far off is the slope?
So I think in this study, they get minus 4/3 slope. But there is an asterisk there. There's sort of lots of free parameters here. You can pick these A, Bs, and lambdas. And there's some other free parameters in the formulation too, where you can reweight certain triads proportional to where they are in K-space. So I think more recent papers have been able to tune those things to get a 5/3 slope. But in this paper, that's not what they found, with just the simplest form that I showed before. Yeah.
I have the same question for the structure function scaling, right? The exponents should change from Kolmogorov.
Yeah. That's right. So I think, so they don't see that. I mean, they see sort of this sign of intermittency in the viscous range, but not in the structure functions. Yeah, that's right. I think, I'm not positive off the top of my head, but I think most of these simulations are using, one of the lambdas there is the golden mean, so 1.6 something. So it's a pretty coarse grid in Fourier space, and the resolution is very small. So it's only something like 20 modes in each dimension, because you don't need many to span a large dynamic range of length scales. So it could also be associated with something like that. Okay, so that's isotropic turbulence. So there's also been work from De Bruhl's group applying this to homogeneous convection. So this is looking at Rayleigh-Benard, but with vertical periodicity. And these are their results showing that the Nusselt number scalings that they find is a function of Rayleigh number. So since they don't have walls, they need to put in a large-scale drag to saturate the flow. And they say that modifies some things at low Prandtl number. But in general, they do see this regime where they see a Rayleigh 1/2 scaling, sort of following the ultimate regime prediction for the Nusselt number there. So more recently, they also did rotating turbulence on, again, in the homogeneous setting. And again, 3D log lattice. I think they also used this golden mean for the lambda ratio. Again, they need a large scale drag to equilibrate the solution, but then they see the geostrophic and ultimate regime scalings there.
How do you?
They claim to.
Yeah. But if you have trouble going back to a sort of physical grid, what's the way in which the Nusselt number is calculated?
The Nusselt number here, I think it's just using the means, right?
Oh,
the mean
okay,
defects.
yeah. Oh, yeah. I see.
So you still have like a k equals 0 wave number. So you can still do an average by basically throwing out all the deviations from the horizontal mean. Yeah. Okay, so there's been lots of work to apply this in the homogeneous setting, but they weren't invited because there's no boundaries there. So I wanted to do this with boundaries and apply this to Rayleigh-Benard, but actually with walls top and bottom. Okay, and the challenge there is that to do high Rayleigh number simulations of true Rayleigh-Benard convection, you need an extreme dynamic range of length scales, not just in the horizontal, but also in the vertical. If you're used to running Rayleigh-Benard simulations, you might be used to thinking like, okay, I only need fine resolution at the boundary layers in the vertical. So something like a Chebyshev grid can take care of that. But at very high Rayleigh numbers, that's not true, right? You get eddies that are shed into the interior that have the length scale of the boundary layer, and those move far from the boundary layer. So you need that same resolution deep in the interior. So the state-of-the-art simulations, these are 2D simulations by Xiaowei Zhu in Delaflosa's group. So these are finite difference simulations that are basically uniform grid, resolving the boundary layer scale all the way through the interior of the simulation, and then go up to Rayleigh numbers of 10 to the 14, and their finite difference resolution is like 20,000 points by 10,000 points. So you need very high resolutions. You can't just compress everything logarithmically. We also don't really know how to do a logarithmic compression with the two boundaries, again, because of this issue of these incommensurate lambdas. So the log lattice I talked about before isn't easily applicable to the wall normal direction. So the idea that Rich Kurzweil and Steve Tobias and I had was that we could use the log lattice discretization to compress the horizontal in these simulations, right? These are still horizontally periodic with no lateral walls. So we could do log lattice in the horizontal, but we'll still need a traditional discretization in the vertical. And that's hard because of the types of extremely large resolutions that are required if we want to go to Rayleigh numbers beyond what they do here. But luckily, we do have good methods for doing that based on sparse Chebyshev methods. So I'm going to say a little bit about these. So probably most people are familiar with Chebyshev polynomials, but if not, I like to show this picture. So Chebyshev polynomials are really just Fourier series in disguise. So if you take a bunch of cosine modes and plot them over a unit cylinder, and then project that down into the plane, the projections of the different cosine modes are exactly the Chebyshev polynomials, and they're a set of orthogonal polynomials. So basically, they give us a basis that lets us spectrally represent smooth functions on the bounded interval from -1 to 1 with the same properties that Fourier series have. So exponential convergence for smooth functions, the ability to use a DCT, and so on. So this is a really nice numerical tool. The sort of classic and most well-established technique for using these in a simulation is to do what's called Chebyshev collocation. The idea here is basically that if you take an evenly spaced set of points on the cylinder, project it down, then you get a grid that's sort of clustered near the endpoints here. So we think of this as being good for like resolving boundary layers near walls. And we represent the variables in our PDE based on the polynomial interpolant of the values at those points. So if we have some function u at this set of points, we can compute its derivatives by drawing the polynomial interpolant that goes through all those points, differentiating that exactly, and then looking at the values of that on the same grid. So this gives us a discrete, what's called the collocation differentiation operator D, which is the map from grid points to derivative values on this collocation grid. So this is the classical technique that's really nice and works really well, but it's limited in when you start to scale to these extreme resolutions. This D matrix that you get is dense, and as a result of that, the conditioning of discretizations using this approach becomes prohibitive at very large resolutions, like degrees into the thousands or more. Okay, so there's a few modifications that have been developed over the years to work towards these larger regimes. So the first is what's called the Lanczos-Tau method. So this is basically the idea that we should work with the coefficients of the Chebyshev polynomial expansion instead of the values at the grid points. And if we take the basis functions as these Chebyshev polynomials, compute their derivatives, and then re-expand that back in Chebyshev, what we get is not a totally dense matrix, but an upper triangular half-dense matrix like this. So it's a bit better conditioned and a bit faster than collocation, but asymptotically solving it is still more than order n and has poor conditioning. But you can do better. You can do something that's called the quasi-inverse technique. The idea here is to write a Chebyshev series for both our function u and for its derivative. And then we can use this identity of the Chebyshev polynomials to write a recurrence relation between the coefficients of the derivative and the original function. And basically, this gives us a matrix that we can use as a preconditioner that sparsifies that Chebyshev tau matrix D. So this B matrix is sort of encoding this relation between the coefficients of a function and its derivative, and it's the pseudo-inverse of the derivative. So if we apply it as a preconditioner, we get a diagonal matrix out. So this was a method that was developed in the mathematical literature, a few decades ago, but I think it was really Keith Julian who established this as a good tool for doing high-resolution fluid simulations, certainly in the geophysical community, I think maybe overall in fluid dynamics as well. And this really lets you scale these Chebyshev techniques into thousands of degrees for doing high-resolution studies of convection. So the sort of current, most modern mathematical formulation of this idea is called the ultraspherical method, and this viewpoint was sort of popularized more recently by Sheehan Ulver and Alex Townsend. And the idea is you can view that same procedure also as saying we're going to start with a function in Chebyshev polynomials, but then we're going to project it against a different set of polynomials. So we'll expand the equations in a different basis set, ones that are sort of naturally the derivatives of the Chebyshev polynomials. So now if I take my differential operator and expand it in this basis, I naturally get something that's banded. This requires me to use a conversion matrix, though, to apply to operators or terms in the equation that don't have derivatives. And that is a banded matrix like this, which is actually basically the same as the quasi-inverse matrix from the quasi-inverse technique that Keith developed, just up to diagonal rescalings. This is a slightly more flexible method. It's a bit easier to incorporate non-constant coefficients and different boundary conditions using this approach. So this is the technique that we use in the Daedalus code. So I'm going to do a little plug for Daedalus because this is really my day job. So Daedalus is an open source PDE solver that uses this ultraspherical method to give sparse discretizations of general PDEs. So what's sort of nice about it is it doesn't have any built-in equations. It has a parsing framework that lets you enter your own equations in plain text. So you kind of type in here the Busnesque equations, and the code automatically parses that into a solver using Fourier series, spherical harmonics, and these sparse polynomial bases. So this is nice because it lets you do really rapid solver development. You can easily change the terms in your equations, change the variables you're using to formulate them, and so on. It's actually not, strictly speaking, a fluid solver, right? It has no built-in equations. So if you want to solve Navier-Stokes, you have to type them in yourself. But that also means you can solve things besides Navier-Stokes. So you can do these like nonlinear Schrodinger quantum graph problems or other non-fluids things. I think in reality, almost everyone just uses it for fluids. And
as they should.
And the code is also has automatic MPI parallelization. So the idea is that you can try to develop simple models at small scale on your laptop, but then scale them up to run in the cluster. And yeah, I mean, there's lots of experts here, people who've written very nice codes, and I'll say, of course, this flexibility comes at a cost, right? And our goal is to roughly try to stay within a factor of 2 of purpose, like equation-specific codes that other people build and optimize. With the generalized algorithms, it's harder to get closer than that, but so we sort of favor it from the development point of view. And if you have to do funky equation sets that maybe there aren't existing good codes for, this might be a good option. So if you want to learn more, you can just Google Daedalus project. If you're in Europe, you might end up at this website, though, which is the website for the Italian metal band called the Daedalus Project. So that's not the right website, unfortunately. DaedalusProject.org is the right website. Our band photo isn't quite as cool as theirs. But this is the core development group here. So it's myself, Daniel Ekman at Northwestern, Ben Brown at CU Boulder, who are both here, and then Jeff Oishi, who's now at the University of New Hampshire, and Jeff Vassell at the University of Edinburgh.
Is that band any good?
Depends if you're a metal fan or not, I guess. The weirdest thing about it is their specific niche of metal music is mathcore metal music. So that's a great coincidence. Okay, so since I have this picture up, I wanted to share a message from Jeff Vassell, actually, who I think many people know here, but who unfortunately wasn't able to make it to the conference. So he asked me to share this. He just wanted to share this message about Keith. He worked very closely with Keith for many years, and I think really wanted to point out that how appreciative he was of Keith taking him under his wing, and also how I think Keith told him that he was really excited about the IPAM meeting just because of the people that it was going to bring together, that he really cared more about the people coming together here than even what everyone was talking about in particular. I think Bob mentioned the paper I'm showing at the bottom here a couple times. So this was recent work that Jeff published on the rapidly rotating limit of wall mode instability. And this was work that he first did with Keith driving the asymptotics here, I think something like 15 years ago. And it was actually my first project using Daedalus was to try to simulate this in a Cartesian domain. And it was hard, it was very stiff and was blowing up a lot. So it was sort of a back burner project for us for many years as we built in more capabilities to the code and added the ability to do cylinders and so on. And really it was Keith's passing earlier this year that really galvanized us back into action to go back and revisit this work and finish it and wrap it up. So I think for Jeff, it's kind of a tribute to his time working with Keith. And the equation has the paper has like 200 equations in it or something. So I think it's a good tribute to the types of asymptotics that they both really love to do. Okay, so back to the log lattice here. So the idea that we have is to use the log Fourier discretization in the horizontal and one of these sparse Chebyshev discretizations in the vertical to try to do extreme Rayleigh-Benard simulations. So the idea is that, again, our horizontal resolution will go sort of like log of the spatial dynamic range we need, log of Reynolds number. Chebyshev resolution needs to go proportional to that. So that still is going to scale like Reynolds to the 3/4. Same thing with the temporal resolution. But now when you put it all together, the total degrees of freedom in the channel now will go like Reynolds to the 3/2 instead of Reynolds cubed. So it still represents a big savings. And key to this, again, is the fact that the solve is linear in the Chebyshev resolution, right? So you really need the sparse method to achieve that. We're not having to square this term as well to do the coupled vertical solve. So the mode space kind of looks like this. So we're sort of on this Chebyshev grid in the vertical and then on this logarithmically spaced Fourier grid in the horizontal. So we're taking, again, even wave number jumps in log space. And so in linear space, our basis kind of looks like this, right? You're really sparsifying out and including less modes as you move up to high K. Yeah?
Bizarre question. You've got a lot more sampling at low wave numbers.
For sure.
You've got a logarithmic distribution in wave number. What about if you did a logarithmic distribution in wavelength?
Oh, okay.
Is that mathematically just stupid, or is there?
No, I mean, I'm not sure. I mean, maybe it depends on the problem. Like if you were trying to study a problem, yeah, I'm not sure. I haven't thought about that, like when that would be good. I guess the idea here is that, we expect sort of like self-similar behavior in K. So, it's true that you're throwing out lots of modes up here, but that's sort of what you want to do when you increase the Reynolds number, right? You're extending your inertial range a little bit more. And if you use a regular linear spacing, all of your resolution is going into that like one tiny bit of the spectrum that you're extending, right? And so this is sort of like, the way I like to think of this is sort of like maybe like a type of finite volume discretization in Fourier space is an alternative to thinking of it as just a basis set. And you're just scaling the bins in your finite volume space sort of so that they have even sampling in K. I'm not sure if you would want to do that in lambda. Yeah, maybe. Yeah.
A related question. Is it possible to build a lattice such that you dense sampling near the drive scale, dense sampling into the dissipation scale, that's sparse in the inertial?
Yeah, you can. I mean, yeah, you're free to pick whatever things you want. The tricky part is making the runtime complexity fast, right? You have to compute the triads, and it's easy to end up in a case where computing all the triads is like worse than doing the FFT. So yeah, I think it depends on the details, but yeah, I think there's definitely lots of room to explore with different strategies for picking the lambdas here. Yeah. Okay, but this is what we went with. So I guess the only other thing I'll point out here is, again, the homogeneous simulations usually used lambdas 1.6. We tried smaller lambdas because we thought that was a bit too sparse. So we used things kind of between 1.05 and 1.15. So here's an example simulation of non-rotating Rayleigh-Benard. This is kind of where we've done the most work here so far. So again, the simulation gets the right linear dynamics. So early time, it looks the same as DNS. So one of these movies is DNS, and one is the log lattice. On the top row, we're showing the buoyancy, then the vorticity, and the vertical velocity here. These are 2D simulations. So at early times, they look the same. I'm going to play the movies together and see if you can spot which one is the log lattice. OK. It's the one that looks horrible, right? So this is the DNS, right? It gives you these nice classic convection rolls. Looks good. The log lattice simulation, if I play it again, basically as soon as things go nonlinear, the modes completely dephase, and you can't maintain coherent structures, again, because of the non-commensurate lambdas. So the flow morphology looks very different. This might be why no one had tried to plot it before, or at least no one had put a plot of it in their papers before. But it's interesting to look at. But the question is, does that matter, right? So in regular Rayleigh-Benard, if the boundary layer is what's limiting the heat flux, and the Rayleigh one-third scaling is based on a linear argument, essentially, that the boundary layer destabilizes, you might expect that, well, clearly we had some nonlinearity that mixed the interior, but now we have a thin boundary layer, and we have the right linear dynamics. So if we get the same instability, then maybe we'll get the same heat flux scaling. Was there a question? Yeah.
Quick question. You mentioned earlier it's not trivial to go back from the wave number space to real space, but here you're plotting things in real space.
OK, so yeah, it's not. So you still just have, right, U is some sum over K in this lattice set, right? U hat K e to the I kx. OK, so I can plot this, right? Given my coefficients, I'm tracking these coefficients in my set. I can plot this at any x, so I can just evaluate it. The point is that it's not a periodic function over any box length, right? This is just kind of a generic function on the entire real line. So you have to pick kind of an arbitrary place to plot it. And if you see any particular structure, that structure is not going to repeat anywhere else in the real line necessarily, right? Because these lambdas are incommensurate. So it doesn't really make sense to, yeah, so it's a bit fuzzy, but I think, yeah, maybe it's still useful.
Can you play the movie again?
Yeah.
We'll see that now.
Yeah, maybe I can, oh. So, right, so there, and then right as it breaks, you see horizontally non-local things happening, right? Hotspots appear that are not actually seeded by vertical plumes, right? So, yeah, it looks crazy. Okay.
I suppose it's not possible to use cosine sine phase.
Good question. Yeah. So if you wanted to, you could fix the phase of these. And that would be the same as using basically cosines instead of using complex exponentials. And that would give you a coherent phase at one point on the real line, at x equals 0. So you can basically force a left-right symmetry around x equals 0, but there's still no periodicity. So I have played a little bit with that, and that's interesting. You can have one coherent plume in the middle, but nowhere else. Yeah. So I don't know. OK. But yeah, I think that is a cool idea. And people have used that to do, you could also use that to do like one wall in a semi-infinite domain or something like that, to look at a turbulent boundary layer, for instance, and the bottom of a log layer, for instance. OK, so that's the idea. That's what the basic movie looks like at Rayleigh 10 to the 8. But the point is that it's cheap, right? The horizontal resolution is very small to get the dynamic range that we need. So we were able to use this technique and go up to Rayleigh numbers around 10 to the 17, whereas the state of the art for DNS is 10 to the 14, right? And the numbers here are kind of crazy, right? So you see in the ranges that we can both do, we need basically the same vertical Chebyshev resolution as the finite difference code needs, right? But the horizontal resolution is way, way lower, right? Instead of 20,000 finite difference cells in the horizontal, we need 144 log lattice terms. So we can push that up, and at 10 to the 17, we're doing 32,000 Chebyshev modes in the vertical. And again, this is really only possible because we have this like highly banded matrix from the sparse Chebyshev technique. Just for fun, here's a video of Rayleigh 10 to the 14. This is the vertical velocity Again, lambda 1.16. So in the turbulent regime, I don't know. It looks weird, right? It doesn't look like a normal fluid flow. But yeah, I don't know. Something's happening. And it's well resolved if you look at the spectrum. So.
Vertical bands of coherence.
Yeah, so there are k equals 0 terms here, and the horizontal means actually are some of the most active in terms of the triads, because k equals 0 interacts with every other mode. So in general, the power spectrum, you get a lot of power at k equals 0. Maybe we should be filtering that, I'm not sure. And then weaker power at the other k's, which are just interacting locally in the spectrum. Okay, so that's what the videos look like. What about the statistics? So this is a plot of Nusselt versus Rayleigh from these runs going up to 10 to the 17. The black lines are those state-of-the-art DNS from Zhu et al. And depending on which plot you look at, over here, it seems like the log lattice is clearly continuing to follow the Rayleigh 1/3 Malkus scaling. And if you look at the compensated plot, then clearly it's turning up away from the Malkus scaling into the ultimate regime. So I won't make any judgments. I'll pick whichever plot you like, I guess. One thing to point out, though, is that there's this overall factor of 2 that we don't understand. So all the Nusselt numbers across the board, they scale very close to Rayleigh to the 1/3, but they're about a factor of 2 bigger than the DNS.
If you put Niemela on there,
If I put what on there?
Joe Niemela, Bob showed that data. That's roughly up to 10 to the 17. And
Okay, yeah, I should add that.
what is it? Nature Science 2000.
Nature, 2000, Niemela, and Srinivas.
Yeah.
Okay, what aspect ratio?
That's
Half.
1/2.
1/2? Okay, this is 2. I don't know. Yeah, I don't know if there's a strong aspect ratio dependence here or not. That could be part of this
The
factor.
prefactor is even different, actually.
Okay, yeah, we should add more data. This is all that I've plotted so far. Yeah, so I mean, I don't know. It's interesting. You know, it gives us the same scaling. There's lots of knobs that we can still tune, change lambda parameters, and so on. So I think we're still trying to figure out, you know, how trustworthy this is. I'll also mention that the error bars here are not errors in the mean. They're actually the variance of the Nusselt number. One issue is that it still takes a very long time for the large scales to equilibrate. You don't get around the timescale problem here. So these simulations out at 10 to the 16 and 17, we think are not quite fully equilibrated, and the points, these last couple points might still come down a little more. And the anisotropy of the numerics means that it's fast to run in terms of total CPU time, but it's very hard to parallelize. So we still have to run these for basically a month, but they just take a month on like one node instead of a month on many nodes. So it's still hard to iterate quickly. Okay, so that's the results that we had for non-rotating Rayleigh-Benard. And we thought, okay, well, just add rotation. How hard could that be, right? So these are the kind of preliminary results for rotating convection. And like, obviously, it ended up being much harder than I thought. So we're not as far as we wanted to be, but I think there are a few interesting things to show so far. So this is a movie of the simulation, again, buoyancy, vorticity, and now in-plane velocities. This is 2.5D, again, log Fourier, Chebyshev, for Rayleigh tilde 40, Ekman 10 to the minus 6, and then the horizontal domain is 10 times the critical wavelength. And again, the same lambda is 1.16.
What's 2.5 mean in this case?
2.5D, so the discretization is 2D. It's just log Fourier in X, Chebyshev in Z, but we have velocity into the board also. So we have 3 velocity components, 2 dimensions of variation. Okay, so I'll play the movie. Again, it kind of looks crazy. What happens is there's an initial instability at the expected linear instability length scale, but then the system enters this like strong relaxation oscillation period where there's sort of a well-mixed interior, heat is diffusing in from the boundary layers. At some point, there is an instability that forms there, and then that shoots off and mixes the interior again. So it's very strange. It doesn't look very turbulent, but this is pretty modest parameters, I guess. So if we look at the Nusselt number is highly variable in time, indicating this strong temporal intermittency. And I think this looks pretty different than what we expect. But I actually don't know good references for DNS here to compare to. So if anyone knows that, I'd be very interested in 2.5D DNS in this regime. Anyways, we can still, despite this variation, what's really surprising is we can compare the Nusselt number to a reference. So the measured temporal average of the Nusselt number here, despite these large variations, is about 16. And the reference, which is from Adrian's paper, is 15.8, plus or minus 1.
What's the aspect ratio?
So this is, here it's 10 times the critical length here. So this is the same parameters as Adrian's work, so I'm using his DNS as the reference here for Nusselt numbers. And I don't know, so that maybe this is just a coincidence, but it's remarkably close. Oh, whoops. It's remarkably close to the average. So there could be some sort of critical argument for why we see that same Nusselt number. Obviously, we want to go to lower Ekman numbers. The difficulty is that this temporal intermittency just gets worse and worse. So at Ekman 10 to the minus 7, you get these now several order of magnitude spikes and variations in the Nusselt number. So it's extremely strong bursty dynamics. And this is really difficult to do time stepping with. I can talk a little bit more about that at the end if anyone's interested. But adaptive time stepping here is very hard because of these issues of it's not clear how to compute a CFL, basically.
Sorry, what are the bursts again?
So it's this motion. So we have an initial linear stability. If you focus on the top here, the buoyancy, you sort of go between a mixed state and then instability kicking off and remixing as the stratification is reforming from diffusion from the boundary layers. So you just get this, yeah. That's what it looks like. The color bars here are running with the amplitude. So the velocity is basically going to 0 and then growing back up, saturating again. But you can see it most clearly in the buoyancy field. Yeah, Brad?
I'm not sure if you said, what direction is the rotation?
It's vertical, yeah.
So these look like walnuts.
No, it's periodic. Well, it's not periodic. It's whatever this is.
Wait, why? Can you explain again? Why is it 2.5D? What did you do?
Yeah, so we have a velocity vector, which is u, v, and w, and those depend spatially just on x and z. Okay, right? So we have Coriolis acting between u and v, but those don't vary in y.
So then you
So it's
does
like
that
a-
mean you have zonal flows into the page?
That's the only, yeah, this is only zonal flow dynamics based.
And do the zonal flows somehow kill the convection?
Probably, yeah. I think
That's your
a
oscillation.
lot of this might be an artifact of 2.5D for sure.
That's what I
Yeah, but it's amazing that, I don't know, it gets the right Nusselt number on average, even though it has this crazy temporal
Do you
intermittency.
think that's just because it's getting the dominant scale?
Yeah, I don't know. It could be, yeah. So, okay, so at 10 to the minus 6 again, good Nusselt number. Then the intermittency grows, and it's really hard to do anything below Ekman 10 to the minus 7. But still at this one, the Nusselt number is remarkably close, even though it has this extremely large variance and has maxima that are orders of magnitude bigger than the average. Okay, so extreme parameters turned out to be difficult. That's why I put extreme in quotes in my title. But what this does let us do is still extreme dynamic range of spatial scales. So I can go back to Ekman 10 to the minus 6, but in the log lattice, it's actually very easy for me to increase the domain size, and we can, just by add more modes at lower wave numbers, and we can go up to now a horizontal domain size that's 10,000 times the critical wavelength. So this simulation is basically twice as expensive as the other one that I showed. Right, that's the real power of the log lattice here. The results are not much different. I mean, you still get this very strange bursting dynamics. And at least to the time that we run this to, we don't see any large-scale structures forming in the simulation. But I think that may just be an artifact of sort of this weird regime we're in that's really not very strongly nonlinear. It doesn't really look turbulent. And it's probably highly constrained by the 2.5D. But the Nusselt number is a bit different there. It's measurably different and lower than the smaller domain one. So.
Sorry, what was the small? Wasn't it 15.6?
It was, yeah, no, it was 16. Yeah, so slightly smaller.
So does the Nusselt number essentially, the uncertainty that you show there, That's just the band of the oscillation and the top and bottom of that oscillation.
That's right. It's the temporal variance. I'm calculating temporal means and variance. Yeah.
It's really just because it's oscillating back and forth.
That's right. Yeah, it's not the error in the mean. I mean, the error in the mean is very small. Yeah. Okay, so that's kind of where things stand with the rotating case. Yeah, I think we're very limited by these strong oscillations. I hope that's just an artifact from 2.5D, and that by going to 3D we can fix that. Again, there might be some other fixes with adaptive time stepping. And I hope we get it working, because I think if we can get a geostrophic turbulence simulation here like we had for, or in a regime kind of like we had for non-rotating Rayleigh-Benard, then it would let us do unique things by examining the large scales. And that's really inaccessible to any other numerical techniques here. Just a couple words about extending to 3D. So we haven't done any 3D yet, but 3D here is very tempting because you get an even larger relative speed up versus DNS, right? Because now you have 2 dimensions that are compressed. It's hard numerically because the numerical domain is now extremely anisotropic, right? We basically have like 100 modes by 100 modes by 32,000 modes or something. And that's really hard to parallelize. So the current Daedalus MPI parallelization strategies can't be directly applied to this. So I'm working on new parallelization strategies to accommodate that. But once we have that, I think it'll be relatively easy to go to 3D. So in the Rayleigh-Benard, for instance, right, it'll only be 100 times harder than our current simulations to do 3D at the same Rayleigh numbers. So beyond that, I think there's still a lot of work that we could do with varying the lattice parameters and the types of lattices we use. Again, we sort of optimized that choice of 1.16 for Rayleigh-Benard and just directly applied that to the rotating case. It might be, though, that choice is flow dependent and that you have to recalibrate this for different flows because of the different types of interactions in Fourier space in different flows. So that's obviously not ideal, but maybe it's just a little more work for each model before you get something that really scales well. Okay, so just to summarize, yeah, this log Fourier lattice has been, I think, a very fun thing because it's sort of a new alternative to DNS for highly multi-scale problems. It has pretty good results for homogeneous flows, and we're trying to mix it with more traditional bases for bounded domains. We saw nice results for non-rotating. Rotating is still in progress, but I think there's lots of open things to try. And hopefully someday this will help us answer the question of what is the true Nusselt number and Rossby number in rotating convection. All right, thanks.